Vehicle emissions have been reducing over the years as a result of the very hard work that engineers have been putting into reducing those emissions. Modern legislation, the introduction of real driving emissions, means that we now have to think about more of the transient behaviour of the system. Things like cold starts, accelerations, decelerations in real-world driving. We need to be able to record data at a much higher sample rate. So we can really get down to the fine detail of what's happening on the engine, what it's doing, what's behind the emissions that are being produced, and the physics that affect those emissions.
Cambustion in Cambridge has been accurately testing emissions in a lab-based environment since 1987. And now that same fast response technology is going out on the road.
Okay, so we've got our test vehicle already fitted with this 2-channel fast NOx analyzer. We'll be taking engine out and tailpipe data simultaneously. And this is the same main control unit that can be used in laboratory, and it's supported by these 2 accessory boxes. These 2 conduits connect the units that are in the rear of the vehicle to 2 sample heads, and these contain the detectors. They're positioned very close to the points in the exhaust that we want to sample from, both before and after the catalyst. We're taking our engine data, simultaneously logged to the same file from the diagnostics port, and we're using a dash cam to record the traffic conditions which might be causing these transient events. And finally, we use very accurate GPS. Combined with our fast emissions gives us centimetre accuracy of where the emissions have been deposited on the road. Right. Should we take it out on the road?
There we go. We can see straight away that there is almost no catalyst conversion efficiency at the cold start, but we're able to measure all of the very high frequency details of each of the engine firing cycles. You can see engine out emissions in blue and tailpipe emissions in green. As the catalyst starts to heat up, we start to convert NO and the tailpipe emissions are reduced. But as we pull away from a set of traffic lights or over a speed bump or from a roundabout, you have transient operation which doesn't favour the catalyst, so NO is leaked through to the tailpipe. So as we decelerate into the speed bump, lambda goes to infinity as combustion stops, and then as we pull away after the speed bump, we get some lean excursion which causes a spike of emissions. This measurement using very fast response analyzers highlights that you can measure these very short duration spikes of emissions very accurately. So we're currently driving down a street in Cambridge which has employed speed bumps to reduce the average speed through this residential neighbourhood. But as we go over each of these speed bumps, we're identifying some large emission spikes which will clearly be adversely affecting the air quality in this residential neighbourhood. So Matt, I wouldn't say that the way you're driving here is particularly unrepresentative of the way the general public drive, but the way that the congestion and the traffic flows kind of encourages you to drive in a particular way, which is clearly producing large amounts of emissions.
Right, now we've taken some data on the road, we can bring that back into the lab and begin to process it and look at the fast emissions alongside some engine parameters so we can understand a bit more about why emission spikes occur. Because we're measuring this data from the OBD port as well as real-time emissions, there are no time alignment issues between the data files. Here we're going to look at the very common speed bump. On the bottom axis we have the fast emissions data, and we're tying that up on the top with data from the diagnostic port of the vehicle. Right, I'll just pause it now so that we can look in a bit more detail about what happens when we go over the speed bump. So initially, we can see when we're running steady state with a fairly rich operation that our conversion efficiency across the catalyst is very good. However, as we slow down on the approach to the speed bump and we get this fuel shutoff, we see a drop in the NOx, and when the combustion restarts, it's lean, as we can see here. This causes a spike in both engine out NOx, but also breakthrough into the tailpipe. As you can see, by plotting our fast emissions data on the same time basis as our diagnostic port, we can learn a lot more about how transient emissions occur and the engine phenomena that lead to them.
We've been using the equipment to analyse the influence of lambda oscillations on the production of NOx. The simple fact is that there's no alternative equipment that has got high enough response rates to allow us to get to the sort of level of resolution that we need in order to do that properly.
Being able to measure real driving emissions with fast response times allows you to see the driving conditions which leads to emission spikes. In order to meet emissions legislation of the future, where transients become even more important, Cambustion can provide you with the tools both in the lab and on the road.